Hi, I'm Mike Marin, and in this video, we'll introduce how to check the validity of the assumptions made when fitting a linear regression model. While the assumptions of a linear model are never perfectly met in reality, we must check if they are reasonable enough assumptions that we can work with them. We will be working with the lung capacity data that was introduced earlier in this series of videos. I've already gone ahead and imported the data into R and attached it. We will examine the assumptions for a model of the relationship between age and lung capacity, with the lung capacity being our Y variable, also known as the outcome or dependent variable. Recall that we can produce a scatter plot of age versus lung capacity using the plot command. Also recall, in earlier videos, we saw we can fit a linear regression model using the LM command. Here I will fit a linear regression model predicting lung capacity using age, and we will store it in this object MOD. We also saw we can ask for a summary of the model using the summary command. Here we can see estimates of the model slope and intercept along with other summaries for the model. Finally, we saw we can add the regression line to this plot using the AB line command. Here we'd like to add the regression line for our model. You'll recall that the regression line can be thought of as the predicted or fitted Y value, which is labeled Y hat. This can also be thought of as the mean of Y given X. This can be expressed as the intercept, or B0, plus the slope B1 times X. The residuals, or errors, are labeled with an E and are the difference between the observed Y value and the predicted or fitted Y value. The standard deviation of these errors or residuals is called the residual standard error in R and is presented in the model summary. This gives us an idea of the average or typical sized error or residual. The residual or error terms are very useful for checking the model assumptions as well as other things about the model fit. You'll recall that a few assumptions are made when fitting a linear regression model. The first assumption is that the Y values, or the errors, are independent. The second assumption is that the Y values can be expressed as a linear function of the X variables. The third assumption is that the variation of observations around the regression line is constant. This is also known as homoscedasticity. The fourth assumption is that for a given value of X, the Y values, or the error terms, are normally distributed. The first assumption requires knowledge of study design or data collection in order to determine the validity of this assumption. The second, third, and fourth assumption can be checked by examining the model residuals or errors. R has a set of built-in regression diagnostic plots, 4 of these in total. These can be produced by asking R to plot the model that we fit. You should note here that this will produce the diagnostic plots, not a plot of the model fit itself. We can see when submitting this command, we're asked to hit return to see the next plot. When we hit return, we can see the first plot here. This plot is known as a residual plot. Here, the x-axis is the predicted or fitted Y values, the Y hats. On the y-axis is the residuals or errors. If the linearity assumption is met, we should see no pattern here. The red line should be fairly flat. If the variation is constant here, we should see no pattern. These points should look like a cloud of points. We can take a look at the second plot. This is known as a QQ plot or quantile-quantile plot. The y-axis is the ordered, observed, standardized residuals. On the x-axis is the ordered theoretical residuals. This is what we would expect the residuals to be if the errors or residuals are truly normally distributed. If our Y values, or errors or residual terms, are normally distributed, these points should fall roughly on a diagonal line. The third plot here, as well as the fourth plot we see here, are other plots that can help us to identify nonlinearities, non-constant variance, as well as other troublesome observations. If we would like to have all 4 of these plots appear on one screen, we can change this using the mfrow command. We would like to have the plotting screen split into 2 by 2, allowing us to have 2 rows of plots and 2 columns of plots, or 4 plots in total on one screen. We can see now when we submit the plot model command, all 4 of these diagnostic plots appear on one screen. Okay, let's go ahead and put this back to having only one plot appear on the screen. And now let's take a look at how non-constant variance will show up in a residual plot. I've already loaded a data set where there is increasing variance. Let's take a look at a scatter plot of x versus y to see this. Let's also go ahead and fit another regression model. We'll call it model 2, predicting y using x. Let's go ahead and add this regression line to our plot. When we take a look at the plot here, we can see for larger x values, the variation in y is larger, or the errors or residuals become larger. Let's take a look at the regression diagnostic plots for this model. First, we can take a look at the residual plot. Here, when looking at the residual plot, we can see this sort of megaphone shape appearing. This suggests that variance is increasing. Larger predicted values are associated with larger errors or residuals. We can also see the red line in this plot is fairly flat, indicating the linearity assumption is met. In our QQ plot, we can see the data looks fairly normal. And again, we can see the increasing variance showing up in this other diagnostic plot. Now, let's take a look at another set of data I've loaded where there is a nonlinear relationship. Here we'll take a look at a plot of XX versus YY. And we can see this nonlinear relationship appearing. Let's go ahead and fit a model. We'll call it model 3. That's a linear model predicting YY using XX. And let's go ahead and add this line to our scatter plot. Here we can clearly see there is a nonlinear relationship. If we take a look at the diagnostic plots for this model, when looking at the residual plot, we can see the red line has this curved pattern showing up. There is clearly curvature associated with the residual or error terms. Taking a look at the QQ plot, the data looks fairly normal. And once again, we can see this nonlinearity showing up in our other diagnostic plots as well. You may be wondering, what's the use of making these diagnostic plots if we can see the violations of the assumptions when we look at the scatter plots themselves? Well, when fitting a multiple linear regression model, we will have multiple x variables. We are going to make the same set of assumptions in a multiple linear regression model that we have in these simple linear regression models, except we're not able to produce scatter plots of the data when we have more than 3 variables. These regression diagnostic plots will allow us to check the validity of the assumptions we make when we have too many variables to be able to visualize the relationship between them. In the next video in this series, we'll talk a bit more about examining the model fit. Thanks for watching this video, and make sure to check out my other instructional videos.